Let's see. So this was section P2. It was on exponents and radicals, and I'll get to a section where, most of the questions in the emails were. So it says we can use blank form to rewrite repeated multiplication. What form are we talking about? Okay, exponential form. Okay, exponential form. Okay, exponents are another way to write a multiplication. They're like shorthand. So this number right here, we call that the base. That number right there is the exponent, and I'm just going to write exp for short. Okay, and then how many of these factors of a do we have? How do we decide how many of these we write down? I've got a little dot, dot, dot right here. How do we decide how many we write down? Brandon? By the exponents. So we'll do n factors here. N factors of a. Okay, and what's another common name for an exponent? So a lot of times we'll call it an exponent, but we'll also call it Lynn. We'll also call it a power. Okay? All right, now we're going to take a quick look at these properties and just make sure we're all on the same page. So this property right here, here's how we'd write it down in general, mathematically speaking. If we wrote an example for this, it would be something like this. And of course the answer is x to the fifth, right? Okay, and I'm going to go to this one right here. It's kind of like you can distribute that exponent through to each one of the factors. If there was addition and subtraction in between the a and the b, you couldn't do this. Okay, so please make sure you don't do that. Okay, so an example would be xy raised to the third. You can write it as x to the third, times y to the third, x to the third, y to the third. If it had been x plus y raised to the third, could you do this? X to the third plus y to the third? Nope, can't do that. Classic mistake, please make sure you don't do that. Okay, and an example here, if I had x to the fifth over x to the second, what would my answer be? X to the third. Okay, we subtract the bottom exponent from the top when we're dividing. If we're multiplying them, we add them together. Okay, this is called the power to a power property. If I had x squared raised to the third, over here I add the exponents together. What do I do here? Multiply them together. So we've got x to the sixth. Okay, now everybody's familiar with negative exponents? Okay, can somebody tell me what a negative exponent means? Because you can almost treat that negative right there and that n separately. The n is how many times we're going to use a as a factor. Anybody know what the negative means? Or can you describe it? It's right up there, so can you describe it? What does the negative do? Tammy? Very good. Okay, that negative exponent means reciprocal. Okay, it's the reciprocal. So we can do a couple of things. We can do the reciprocal of the entire exponential form. So we can do 1 over a to the n, and it changes from a negative exponent to a positive exponent. Or we can do this, and this is kind of cool. You could just apply the reciprocal to the a. What's the reciprocal of a? 1 over a. And then you raise that to the n. And you'll notice that if we apply this property right here, you can apply the exponent to the top. So that would be 1 to the n over a to the n. And what is 1 to the n? What's 1 to any power? 1. So this is 1 over a to the n. See how that works? Okay, again, this is kind of like distributing in, okay, and I won't do an example like that. A to the 0 is 1, as long as a wasn't 0 to begin with, okay? So any number other than 0 to the 0 power is 1. And then we've got this example right here. This is interesting, but it doesn't come up very often. If you have the absolute value of a squared, if you square a number, whether it's positive or negative to begin with, what does it always end up as? Always ends up as a positive. So does the absolute value help us at all? Nope. Okay. So it's the same as if you just had an a squared. Okay. And this is an important distinction to make. What is the difference between the two of these? People do this all the time. Nathan?
In the first one, the negative doesn't apply to the exponent, but in the second one, the negative does.
Very good. So you want to make sure you're clear on this little detail. An exponent only applies to what it's over. And it's only over the 3 right here. If we wanted the negative to be included, we'd put that in parentheses. Okay? So the answer on this one is, a lot of people will get this wrong, the answer on this one is -9. And the answer on this one is +9. And do you see why? Very important distinction there. Okay, any questions? Okay. And again, I'm gonna go through pretty quickly. I may not do all of these examples so that you can have time to work. I'm gonna focus on the ones that I got questions on. So if we have something like this, we're going to apply those properties up above. So I can apply that power to every one of these. So I can apply it to the negative, the 5, the x, and the y squared, and then the 2 in the denominator. Okay? So if I do that, I end up with, what's negative 5 squared? 25. X squared. What's y squared squared? Y to the 4th. And 2 squared, get a 4 on the bottom. Then I've got times, I've got an 8, x to the 3rd, y to the 7th. And then I just want to simplify this. What would I do to simplify this? Cancel the 8 with the 4, because technically I could put that over a 1. So I'm going to cancel the 4 with the 8. It goes in there one time, goes in here twice. So I can tell what the coefficient is, what the number out front is. It's a 50. How many x's altogether? 2 here, 3 here, so altogether that's going to be 5. And how many y's? 11. Okay, so that would be the answer right there. What does the negative mean? Okay, the negative exponent, the negative in the exponent means reciprocal. So we're going to do the reciprocal. So this is going to be 1 over 5x squared. Okay, what is this ugly mess right here? It's a 1. So do I even need to write it? Not really, but we will. So this is 1 over, this is going to be 25x squared. Okay? What don't we like about the way this first fraction is written? Okay, we've got some negative exponents. Okay, if you've got a factor with a negative exponent, you can move it from the top to the bottom and change the sign, or the bottom to the top. So we're going to rewrite this as 4. I'm going to put the x squared on the bottom. I'm going to write the y cubed on the top. And the z is fine, it gets to stay on the bottom. Do I need to change this at all? I do. The y squared is fine. The 16 is fine. But I need to move that to the top, so that's going to be a plain old x. And I need to move that to the top, that's going to be a z squared. And then I can go through and I can cancel, simplify, and all that sort of stuff. Any questions? Okay, I'm not going to finish that one. If you don't know how to finish it, come see me afterward. Okay, what does the negative in the exponent mean? Reciprocal. Do I need to clean anything up before I applied that reciprocal? Yeah, it would probably be better if we did this. 2x y squared over z, and then we raise that to the negative 3. Now I'm showing a little bit of extra work, because what I could do is I could do z 2x y squared, and then raise it to the 3rd, and then you can finish that, right? We'd apply that exponent to that, and that. Any questions? Okay, there's this little topic that they threw in this section on scientific notation. Scientific notation can be used to write really big or really small numbers in what form? Exponential form. Okay. Really big numbers will have what type of exponents? Positive exponents. And really small numbers will have negative exponents. Okay? Now, can somebody tell me what's the key to writing, or how would you write this number right here? That's how many inches it is to the sun, approximately. How would we write that in scientific notation? What do you have to be careful of when you're writing things in scientific notation? The decimal. Where do we put the decimal? Raymond?
You put decimal, so you have your ones number and then decimal.
You have to have one digit other than a 0 in front of the decimal, okay, and everything else behind. So we want to move the decimal from right here all the way over to right there. So we're going to do 5.9 times 10 to the, and then we just count how many places did we move the decimal. So there's 3, 6, 9, and 12. So this is going to be 10 to the 12th. Okay? If I have 1.6 times 10 to the negative 13, is that a big number or a small number?
Small.
Very small number. So this is the approximate diameter of a proton. We're going to take that decimal, if we were to write it in a standard numerical form, and we're going to move it how many places? 13, which direction? To the left. So we're going to move it over here. Now, quickly tell me, how many zeros am I going to have? Careful. That's one place, so in front I'm going to have 12 zeros, then a 1, 6. Okay? That's it. Okay? All right. Any questions? Okay. Roots and radicals. There's some vocabulary words that you've heard before. We kind of use them interchangeably, and you should know what the distinctions are. Okay, that symbol right there is called a radical sign. Okay. Did anybody catch in their reading what that little number in the little crook of the radical sign is?
The index.
Very good. Okay, Noah got it. It's called an index. Okay. The index tells you what type of radical or what type of root you're looking for. Anybody catch the name of the number underneath there? Raymond? Not the base, close.
Root.
It's really close to this word. Hope. Radicand. Okay, so that's called the radicand. Radicand. Again, maybe you win Jeopardy someday, teen tournament or something like that. Okay, and this right here is we're going to call it the nth root. Nth root. Okay? Now, this is something, I learned something when I was reading this textbook. I've been spelling principal wrong for quite a while. I know what a principal root is, but I've been spelling it wrong. I use the other type of principal, so I got that figured out. Principal roots are roots that have the same blank as the radicand. So let me give you an example. A lot of times at the beginning of the year, I'll put a problem like this on the board, or it will just come up, and somebody will say the answer is plus or minus 2. And people look, yeah, I've heard that before. Square root of 4 is plus or minus 2. Got to be a little bit careful with that and stuff like that. Is that right? It's not right. Okay? If the problem was written like this, the answer is just positive 2. And that's because of this idea of a principal root. Okay? A principal root has the same sign as the radicand. So if you see a problem like this, square root of 9, your answer's 3, not plus or minus 3. If you were solving an equation like this, x squared equals 4, and you put the square root in the problem, then what's the answer? Then it's plus or minus 2. If the root was in there to begin with, they're asking for the principal root. Okay? If you put it in there, then you've got to be aware of a couple of them. Okay? And then there are these properties of roots, all of which are pretty darn cool. Okay? This one right here, this is the nth root of a to the m. What this means is you can slide that exponent, if that's the root and that's the exponent, you can slide that outside. You can find the root of a fairly small number and then raise it to the power. If I have the mth root, this sounds a little bit weird, but this is how they talk. Mth root of the nth root of a, you can just multiply those two indices together. And we're going to show why that happens in a little bit. I think we come across a problem that does that. Okay? If I have two of the same root, different numbers, I can write it as one single one, so I can multiply those together. Okay? So if I had the square root of 7 times the square root of 3, I could write that as the square root of 21. Okay? And what if I have the nth root of a and I raise that to the nth power? What do I get? Just get a. Okay? So an example would be something like this right here. 6th root of y to the 6th, what should the answer be? Should just be y. And 3rd root of x to the 3rd? Should just be x. Okay? This is a cool property. And notice that these are all equations, so they go both ways. If you have a nth root on the top, say a square root on the top and a square root on the bottom, you can write it as the square root of a fraction. Or what we normally do is we normally use it in this direction. Okay? We'll take the square root of the top, or the nth root of the top, and the nth root of the bottom, figure them out separately. And again, they always put that in there. Remember, if you've got division, you've got to be careful that you're not dividing by 0. okay? And this right here, it says if n is even, so if we're taking the nth root of a to the n, they don't quite undo each other. If it's even, we have to put an absolute value on there. And if it's odd, it's just exactly what the number was. So let's take a look at the two of these. Did we get this one right? We did. Did we get this one right? Okay, we have to be a little bit careful with even roots. Okay? The answer to an even root is never going to be negative. Since we're not sure what y is, since it was a variable, we should technically put absolute values on there, just to make sure that we got it right. Okay? Now, do I need to do square root of 81? It's 9, right? Cube root of negative 27? Negative 3. Cube root of 64 27ths. Tough to figure out what it would be for the whole fraction, but we can figure it out like this. Cube root of 64 over the cube root of 27. What's the cube root of 64? It is 4. Very good. And cube root of 27? 3. Okay, so we can do those separately. Fourth root of 16? 2. Can you do the fourth root of negative 16? Nope. Can't take an even root of a negative number. We run into one of those domain issues. So we're going to say this, DNE. What does that stand for? Do not enter. Does not exist. Does not exist. Very good. Okay? All right, and let's take a look at this one right here, just using that product property. I can write this as the square root of 16, which has an easy answer. And this one right here, plain old 5. Easy enough, right? Any questions? Okay. When simplifying radicals, we take out groups of factors. So when we're taking square roots, we're going to take out factors in groups of how many? We're doing a square root. Groups of 2. Cube root, we'll take them out in groups of 3. So let's take a look at an example, okay, just to make sure we're all on the same page. The way we do a problem like this is we factor this. So this is going to be the square root of 2 times 3 times 3. It's a square root. So anytime we have a pair of factors or groups of 2, we can take those on the outside. So I'm going to have a 3 on the outside and a 2 stuck on the inside. Okay? Why could I take the 3 out? Because there's 2 of them. Why is the 2 stuck in there? Because there's only one. There's not another one to pair it up with, and that's the answer. Okay, cube root of 24. So we're looking for groups of 3. This is 2 times 12, which is 2 times 6, which is 2 times 3. Group of 3 2's, so 2 on the outside, 3 stuck on the inside because there's nothing else to triple it up with. And have I written the answer correctly? I haven't. Please make sure that the index is the same. Please make sure we're finding the same root. Okay, that's an important point. Okay? This is going to be 2 times 27. And the nice thing about this is, if you think of it this way, 27 has a nice cube root. So the cube root of 27 is 3. That can go on the outside. And there's a 2 stuck on the inside. Kept the numbers fairly small and pretty easy. Okay? And then on this one right here, we're looking for groups of how many? Groups of 4. 16 is 4 2's, so there's a 2 there. Do I have any x's I can take out? Yeah. How many groups of 4 x's do I have? 1 group, so that's going to be x to the first on the outside. How many groups of 4 y's do I have? 2, so that's going to be y squared on the outside. Fourth root of what is stuck underneath? Just 1x. Okay? Any questions? Okay, go ahead and flip the page over. We do like to combine radical terms. They have to be like terms. And if they're going to be like terms, they have to have the same blank and the same radicand. Same index. Or I'm going to say this, just to keep it snappy. They have to have the same root and the same radicand. Okay? So these two problems right here don't look very good right now. But if I simplify this, this is 3 radical 2 with a 4 in front, right? So I get 12 radical 2. And this is going to be 2 radical 2 with a 5 in front. So this is negative 10 radical 2. Do they have the same root? Is it the same index? And do they have the same radicand? Yes, they do. So the answer on this one is just 2 radical 2. Okay? Any questions? Okay. Let's take a good look at this, and before we actually plow through and try and combine the two of these, is there any way we'd be able to combine these? No. Doesn't matter how this ends up looking, because that's a cube root and that's a square root. We're not going to be able to simplify the root at all, or the index at all. It's not going to change numbers or anything. So there's no way we're going to be able to combine these, but we could simplify this. This would be 14 cube root of 3. Took out an 8. That would be 1, 2 on the outside. And this is a square root of 27, not a cube root of 27. So that means I can take out a 3. So this is going to be plus 15 and cube root of 3. Sorry, square root of 3. That's a square root of 3. That's a cube root of 3. Can't combine them at all. Whoops. Okay, any questions? Okay, we're now to the point where I got a few questions in the emails. We usually don't like to leave blank under radicals or leave radicals in the... So what don't we like to leave underneath radicals? Fractions. We don't like to leave fractions underneath radicals. There's nothing wrong with it. It's just by convention, and if we have to use them again later on, it would be better if they weren't there. And we also don't like to leave radicals in the denominator. Don't like to leave radicals in the denominator. Okay, and this involves something called rationalizing. Okay? Okay, so in a nutshell, if we say rationalize the denominator, we're trying to make the denominator into what type of number? I talk about this very informally. We want to make it a nice number. Okay? Something that's easier to work with. It's hard enough to work with fractions, but who wants to get common denominators of radical 8? Okay? That's a big pain. So let's take a look here. If we do this one, this would be 5 on the top and 3 radical 3 on the bottom, right? So we didn't like the fraction underneath the radical, so we simplified it, but we still have a radical in the denominator. Now, why is that 3 stuck underneath there?
Because I can't factor it.
It's completely factored. There's not another 3 to go with it. If I'm simplifying a square root, I need groups of how many? Groups of 2. So I need another 3 underneath the radical. So if I multiply the bottom by radical 3, that would give me two 3's underneath the radical. But can I just multiply the bottom by radical 3? No, I've got to multiply the top by radical 3 also. So here's what I get. I get 5 radical 3. What is radical 3 times radical 3? 3. And I've got 3 times 3. What's the bottom? Bottom's a 9. Now, a lot of times somebody will look at this and they'll say, hey, can I cancel the 3 with the 9? Nope, because it's not a 3, it's the square root of 3. Plug it in your calculator. It's a really ugly number, 1.7 something. Okay? All right, let's take a look at this one. 7 over 2 radical 2. What else do I need here? How many more 2's, how many more radical 2's do I need? I need 1 more. Okay, I'm not going to finish this one. I'm just going to write what you'd do to simplify that one. That's how you rationalize that. Okay, these two are kind of interesting. If you can do these, you can figure out any of these simple rationalizing problems. This is radical 7x. Do I have anything I can take out here?
Y.
I can take out a y. Okay, what do I need?
Radical 3.
I need a radical 3. So this is going to give me on the top, this makes it look even worse. This is 21x on the top. What's on the bottom?
3y.
3y. Okay? Any questions? Okay, take a look at the next one. Okay, the next one is a cube root. It's the exact same expression. We're going to have the cube root of 7x on the top. Can I take anything out of the bottom? What's that? Nothing, right? I only have 1 3. How many do I need? Okay, I need 3 altogether. I have 2 y's. I need 3 altogether. So here's what I've got. I've got the cube root of 3y squared. Now, I heard some people saying what we were going to do. That's great. If I need 3 3's in order to take those out, how many more do I need? I need 2 more, right? 2 more 3's would be a 9. So everybody good with that? If you want to write it as 3 times 3, that's totally okay. If I have 2 y's and I need 3 altogether in order to simplify, how many more y's do I need? I need 1. So on the bottom, let's take a look. 1, 2, 3. 3 3's, I can take that out. How many y's do I have now? 3, so I can take that out. And look, we've made the denominator, we've rationalized it, we've made it a nice number. I'd much rather work with 3y in the denominator rather than cube root of 3y squared. Okay, and then the numerator, let's just figure out what this is. It's still a cube root. Make sure you get the index right. This is going to be a 63xy. Looks ugly, but that is the simplified answer. Okay, any questions? Okay, let's take a look at these problems right here. This is how we rationalize if we have more than one term. Okay, and we're actually going to spend some time in the next couple sections. We talk about polynomials and factoring and stuff like that. If we do this problem right here, we multiply by its, anybody remember the name of it? I heard it back there. Who said that? Hope, what is it? It's called the conjugate. Okay, so it's called the conjugate. Conjugate is a fancy name for a factoring of a difference of squares. This is what we multiply by. And the reason we do that is, if we multiply the two of these together, here's what we get. I get 16. I get plus 4 radical 3. When I multiply here, I get minus 4 radical 3. And then I get negative radical 3 times radical 3. That's going to be negative 3. So what happens is those middle terms go away. I've got a 4 radical 3 and a minus 4 radical 3. They're gone. What is the denominator? Just 13. And the numerator, that's 8 plus 2 radical 3. Again, it's not that this looks any better than the other one. In fact, the numbers here are bigger than they were before. But what advantage does this new simplified part have over the original one, Raymond?
There's no exponent in the denominator.
There's no radical in the denominator, okay? Yeah. And that's what's nice. The denominator is a nicer number. I'd rather work with 13 for a denominator than that right there, okay? Are there any questions? Okay, what's the conjugate here? Radical 5 plus radical 3. And you have to multiply the top and bottom by the same thing. So that's what we're going to multiply by. And the cool part about this is you should be able to figure out what the denominator is without too much trouble, because it's always going to be a perfect square of the first one. What do you get when you square radical 5? 5. Remember we talked about that? If you're squaring a square root, you get whatever's underneath the radicand. Minus, it's always going to be a minus, 3. It's whatever these numbers are right here, if they're both radicals. Okay? It's the square of this one minus the square of that one. That's why it was 16 minus the square of radical 3 is 3. That's why the denominator there turned out to be 13. So the denominator here is 2. Okay? And then the nasty math turns out on top. We'd have to multiply here and then multiply here. Okay? And then collect any like terms of which I don't think there are any. You're going to end up with radical 30. Let's see, plus radical 18, plus 2 radical 2, plus 2 radical 5, plus 2 radical 3. And can you simplify any of those? Not this one, not that one, and not that one. You can simplify that one, okay? So before you circle that and say I'm done with it, you'd want to make sure you simplified that all the way, okay? And last couple topics here. This comes up occasionally in calculus. Okay, this looks good according to the rules that we're used to working with, but occasionally it's useful to rationalize the numerator. So we just want to turn the top into a nice number. Seems a little bit weird that we'd make the top look nice and screw up the bottom, but what would we multiply by? 5 squared of 2 plus 1, 5 squared of 2 plus 1, and then we do the same thing we did before. Okay? So now the top's going to be a nice number and the bottom's going to be kind of ugly. And you could finish that, right? Okay. All right. Okay. Roots can also be expressed as rational exponents. Okay. And what does the word rational mean? Fraction. Okay. Fractional exponents. So the nth root can be expressed in a couple of convenient ways. So if I have a to the 1 over n, that is the nth root of a. And the cool part about this is, so you can either use the radical or you can use the rational exponent, the 1 over n. If you combine that with some of the other exponent rules that they talked about and properties that they talked about in this section, you can take any rational exponent and you can change it into a radical. So this right here is the root, and that right there is the exponent. So the n would go outside, a to the m would go underneath. And I kind of like to think of the m and the n, I kind of like to think of them just kind of turning clockwise like this. So the n would be here and the m is there. And I think I pointed this out earlier. The nice thing about this is you can either have it here, the a to the m underneath with the a, or you can find the nth root of a and then raise it to the m. All three of these are equivalent. Whichever one works best is the one you'd want to use. Okay? Any questions? Okay. Again, whatever is convenient or whatever matches the instructions. And don't forget that you can use the rules that you learned here. I mean, everybody knows this one right here. You can also use it if they're fractional exponents. So if x to the x squared times x to the third equals x to the fifth, x to the 2/7 times x to the 3/7 would equal x to the 5/7. If you add these together to get that answer, you do the same thing here. Okay? It's just a little bit worse, right? Okay, write as a radical and simplify. So this is going to be, that's the root, and that right there is the exponent. So this is the cube root of 125 squared. Now, is that the best way to write that expression right there? Yeah. Probably be better if we did this. 125 and then square that. Because what is the cube root of 125? 5. 5 squared is 25. Okay? What's the index here? 2. A to the third. Can that be simplified at all? How many say yes? How many say no? Okay. Nathan, how do you simplify this?
Since there's 3 a's, you can take 2 and a out.
Perfect. Exactly right. It's a square root. We're looking for groups of 2. Do we have a group of 2? Yeah, we've got 3. So I've got an a on the outside, and then I've got 1 left on the inside. That would be simplified. Okay? Okay. I like this little numeric expression right here because it will allow us to explore all 3 parts of an exponent. What does the negative mean? Reciprocal. What is that? That's the power or the exponent. And what's the 2? That's the root. So let's do the reciprocal. 1 over. That takes care of the negative part. What's the root? Square root of 9. Okay, that's all of those parts represented. There's the reciprocal, there's the root, there's the exponent. So if I'm going to write this number, what am I going to write? 1/3. Pretty ugly way to write 1/3, but that's what it is. Okay? Okay, would you write that one in radical form? Write this one in radical form? And be a little careful. Negative cube root 64. Should I square it underneath or should I square it outside? Probably outside would be better. Okay? Cube root of 64, 4 squared with a negative in front. The answer to that one is negative 16. Okay? So as you're going through, there are lots of these that you'll look at and go, oh, I think I know the answer. Okay? But you want to make sure that you get it right. Okay. Any questions on those? Okay. Right is a rational exponent. 10's the base. Where do I put the 5? Top or bottom? Top. So 5/3. 9xy. That's clearly the exponent, and that's the root. Nobody has an issue with this? Thank you, Hop. We do need the parentheses. Okay? If we didn't have the parentheses, so if I got rid of those parentheses, what does the exponent apply to? Only the y. We want it to apply to all of those, so we'd want that in parentheses. Okay? Any questions? Okay, and then just a few more where we want to simplify these and make sure we get these right. These are kind of interesting problems. Maybe regardless of your background, maybe you haven't seen something like this. I'm looking for groups of how many? Groups of 12. Okay, do I have any groups of 12? Nope, so can I simplify it? Certainly doesn't look like it. But here's the cool part. There are times when working and thinking of things in terms of radicals is really good, and then other times, even if you don't like fractions, working with rational exponents is better. So let's take this, and let's just do what we did right up above. Let's write it using a rational exponent. So y would be the base, and then I've got this fractional exponent. What goes on the top? 2. And on the bottom is a 12. Now, if we had just written that and said, well, let's just go ahead and do it this way, then everyone would look at this and say, you know, y to the 2/12, there's something that bugs me about that. I wouldn't leave it that way. How would you write it? You'd write it to the 1/6. So this is y to the 1/6, and that would be a perfectly good way to write it. Or, since the original problem was written in radical form, let's write the answer in radical form, and what would it be? 6th root of y. Either one of those would be fine. Those are both interchangeable. Okay, any questions? Sure? Okay. Negative 10. X to the... What should you do with these? If this was negative 2x squared times 5x to the 7th, you'd know exactly what to do with those. We add them together. So what's 1/3 plus 3/4? Holy cow, we got to get a common denominator. That's going to be 4/12 plus 9/12. So this is going to be 13/12. And that would be the answer. Ugly problem here. Anybody know what the answer is? Lynn? 7 to the 1/15. And how did you get that? Yep, you multiply the two indexes. That's the quick way to do it. So this would be the 15th root of 7, or 7 to the 1/15. Okay, another way to think of this is a cube root, so it's to the 1/3 power. That's a 5th root, so it's to the 1/5 power. And in the very middle is a 7. Power to a power, what would I do with 1/5 and 1/3? Multiply them together. Okay, that's how we end up with that property there. Okay, and let's take a look at this one right here. Does anybody know how to do this one? Okay. So the first thing we'd want to do is we'd want to recognize that this is an x minus 1 on the top, raised to the first power. And that negative means reciprocal. So I've got an x minus 1 raised to the first power, and then if I move it in the numerator, this is x minus 1 to the positive 1/2. If I had, let me change colors here, if I had y to the first times y to the 1/2, or if I had y to the second times y to the third, add the exponents here, right? Add the exponents here, right? What do you do here? Add the exponents. So the base is going to be x minus 1. 1 plus 1/2 is 1.5, but Lynn has the right way to say it. What would we say? 3/2. We don't write it as a mixed number. We'd write it as that improper fraction, and that right there would be the answer. Okay? Any questions? Yeah, Hop. So multiply those together? Is that what you're saying? No. So if we were doing this one, we'd write that as y to the 5th. We wouldn't do y times y and then raise it to the 5th. Does that answer your question? Yeah.
Okay, where'd you get the 3 and 3 halves again?
So what is 1 plus 1/2?
1.5.
1.5. But we wouldn't write it as a
exactly.
mixed number. We're going to change that to an improper fraction. So 1 times 2 plus 1, so 3/2. 3/2 is the same as 2. Good? Okay. AB. (15) on top because that's the exponent and that's the index. Ought to have parentheses on it. So that's AB raised to the 5th. And then you could just apply the exponent to both of those. It's the only thing you can do with this. That's about it. That's about all. You wouldn't be able to do anything else with that. This is that one we saw earlier, only it would be 1 over the square root of a cubed. And Nathan showed us how we could simplify that one, so you could go a little bit further there. And then the very last thing, is that true? No way. This would be the square root of 9, so this side would be 3, and this would be radical 5 plus 2. There's no way those two things are equal, okay? So please don't try and make up properties, okay? Doesn't work that way, okay? Stick with the ones that we know. All right, that's it for today. So hopefully that answered all your questions. Please read P2, no, P3, okay? Work on the homework and